Well, welcome this to Monday night calculus. It's got to be night someplace. My name is Curtis Brown. I've got Steve Kokoska and Tom Dick here with me. We're going to be talking about accumulation this afternoon. Really excited to share this problem set with you and a few tips. Stick around all the way to the end of this session. I've got a link for a professional development certificate, so I'll give you a way to get that. And do make note that Steve has got his background there for his AP Calculus textbook. We'll be putting some information in the chat about that here
Thank
in
you.
just a minute. Yeah, really excited for the session. So welcome. The problem set is in the description. So if you're a student or a teacher that's wanting to use this with students, the problem set that Steve and Tom are going to be looking at is in the description. And as soon as we've gone live and we got about 24 hours, then we'll put the solutions out there
Mhm.
sometime tomorrow. All right, Steve,
All
I'll
righty.
turn it over to you.
Thank you very much, Curtis. Great to be with you and Tom again. It is Monday, late afternoon in the East Coast calculus, as I like to think about it now, as somebody
There you
reminded me on
go.
Facebook. We've got some good problems, I think, today, Curtis. Good problems to start your students out tomorrow at 8 a.m. when it's chilly on the East Coast here. As usual, Curtis, I'm going to try to solve some of these analytically, and where I can, I'll use technology. I'll use the TI-Nspire. And Tom is willing to show us how to solve some of these problems, sometimes in a different way, but using the TI-84. So let's see what we can do here with number one. We have this mechanical toy that moves vertically up and down along a straight wire with a velocity given by that expression, v of t. T is measured in seconds, v is measured in centimeters per second, and the initial height of the toy is 120 centimeters above the ground at time t equals 0 seconds. You know, Curtis, when Tom and I we're talking about this problem, I asked him if we could change this in the spirit of Florida, Southern Florida, having an anole running up and down a palm tree, but he didn't like that analogy. He didn't like that. Many people wouldn't get that. So we left it as a mechanical toy. But when I send this to you, the context may change slightly. So what's the height of the toy at time t equal 12 seconds? Remember, this is all about using the definite integral as an accumulation function. So what we need to do is to find the position of this mechanical toy after 12 seconds. Let me see if I can arrow up just a little bit here. There we go. So to find this, I have to use this formula right here, and I'll go into this in a little bit more detail in just 1 second. S of 12, the position of this toy at 12 seconds, is the initial position. I'm going to write above this is S of 0 plus the definite integral from 0 to 12 of v of t dt. So the position at time t equal to 12 is the initial position plus its change in position, which is the integral 0 to 12 of v of t dt. Very classic sort of an example. We frequently see this on the AP Calculus exam on one of the free response questions, which involves particle motion, usually on the AB exam. And I've got an answer here of 114.636. I was talking to an AP Calc teacher actually via email yesterday over the weekend, Curtis. And I just want to remind everyone about this 3-digit rule. Remember, when you submit a final answer, numerical final answer, it should be rounded or truncated to 3 digits to the right of the decimal. When we present our solutions here, I usually present that final answer with 3 digits rounded, but truncated is okay. Anything beyond the 3 digits in that final answer is generally just ignored. So here's how I would get this using technology. And again, I'm showing you this on the TI-Nspire, and Tom will do a little bit with the TI-84. In this line right here, what I did is I defined a function v of t. One thing I just wanted to remind you about is that when I define a function, and Tom does this a little differently than I do, I use this colon equal. That's used for defining a function. Tom often, I think, uses the word define. I use the colon equal because this is similar to or the same notation that one would use in Mathematica, so I'm sort of used to that. And I actually solved this problem on the calculator, on a calculator screen in 2 steps. I found the integral from 0 to 12 of v of t dt. And this is sort of interesting. You'll notice that I put a decimal point in the 12 there, and that's so that I would get a decimal point over here, or a decimal answer over here. I believe that if you don't put a decimal there, the TI-Nspire will actually come back with a symbolic answer, which is quite amazing. You might think about how you would integrate that symbolically. Ooh, I wonder if you could do that one. Let's put that in the chat if you can, Curtis. They don't have to give us an answer, but I wonder what the technique would be to use in order to integrate that V of t analytically. And so what I did in the next step is simply add that answer to 120, and there's my 114. And again, I rounded 0.636. Another way to look at this is visually on a graph screen, and a lot of our students like to do it this way. So what I did is I graphed V of t on the screen over here on the right-hand side on my page 1.2. And you can do a definite integral from 0 to 12 on that graph screen. And I got this minus 5.364, and it's rounded there. Okay, I asked it to give me that answer 3 digits to the right of the decimal. But this is just support that, yep, I got the right answer here. And you can actually see that shaded in region, which in some sense represents the distance traveled, the net distance traveled from 0 to 12. It is this area down here, or this area down here, minus this area down here below the x-axis or below the t-axis. Cool, let's look at part B. What's the total distance that the toy travels between t equals 0 and t equals 12? Again, we frequently see problems like this on the exam. Students are frequently asked to distinguish the difference, find the difference, use the difference between 0 to 12 of v of t dt and the absolute value of v of t dt. And this one, in order to find the total distance traveled, we've got to do this integral, evaluate that integral. And I just did that on the calculator screen and got a 7.621. We could also do this on the graph screen by graphing the absolute value of v of t and doing a definite integral on the graph screen. I didn't do that here. Perhaps Tom will look at that on the 84. There's a part C. There's some interesting things going on here, and I apologize for this, Curtis. I may actually flip back to the first page for a moment. When does the toy reach its minimal height above the ground? Its minimal height above the ground. Well, okay, I left out a couple of steps here, but really what I might do is define a function s of t, which represents the height above the ground. And in order to find the minimum height above the ground, I'd have to find the derivative of that, which results in me having to solve this expression, v of t is equal to 0. Well, I know that v of t is equal to 0 at 0, thinking about that function on the first page. And I know it's e to the minus t is never 0. And so I have to solve this expression, and I did that. And that will occur where t is equal to 3 plus 6n, I believe. Now, I started to create a little chart over here, and again, I left out a few steps because I know a little bit about the nature of that function, v of t. But for n equal to 0, I got a t equal 3. For n equal to 1, I got a t equal 9. For n equal 2, I'm outside 0 to 12. So those are the two values of t that I have to worry about. And if I'm constructing a sign chart, I also have to worry about the endpoints t equals 0 and t equals 12. So if you can see down at the bottom here, I've constructed a sign chart. And again, there is no harm in constructing a sign chart on the exam, but students must interpret that sign chart, must write something about that sign chart in their conclusion. So on this sign chart, I've got some tick marks corresponding to the endpoints 0 and 12, and corresponding to these two values of t, where v of t is equal to 0, 3, and 9. And thinking about that graph on the previous page, thinking about the nature of this cosine function, I know a little bit about that. I know that V is negative, positive, and negative. In my own weird way of thinking about things here, whoops, that should be an X here. I know I have a local minimum because V of t is negative, changes from negative to positive. I know I have a local maximum as V of t changes from positive to negative. And so theoretically here, if I'm doing this, I would have to check at t equal 3 and t equal 12. But I'm going to be a little sneaky about this. I'm going to go back over here and take a look at this function v. I recognize that at t equals 0, the velocity is negative. This mechanical toy is decreasing in height from 0 to 3. And I look at that area enclosed between v of t and the t-axis. And I recognize that as the particle, pardon me, as the mechanical toy is rising or going up, that area is nowhere near as large as the area between 0 to 3. So that I know as it reaches this minimum here at t equal to 3, I know I haven't gone up very far at all. And then I know that at 9, it's difficult to see in this graph, there's just a little bit of area between 9 and 12. And that's smaller than what's over here. So by an area argument, this mechanical toy reaches an absolute minimum when t is equal to 3. So theoretically, what I would do looking at this sign chart is I would evaluate my function s of t at t equal 3 and t equal 12. And I would discover that at t equal 3, that's the minimum height of this mechanical toy. And let's see if I've done everything correctly. I'm going to find s of 3 is 120 plus the integral from 0 to 3 of v of t dt. And that turns out to be over here, I believe, 113.513. Now, I think another way, a cool way to attack this function, and even the TI-84 can do this, is I've actually defined a height function for this mechanical toy to be 120 plus the integral from 0 to t of v of x dx. Remember, I'm going to use a different variable, a dummy variable inside that integrand. And over here on this graph screen, I've actually graphed s of x. Now, I've gone a little bit farther to the left and farther to the right here. But I then asked the TI-Nspire to find the minimum of this function s over the interval from 0 to 12. And it came back and gave me that it occurs at time t equal 3. And there's the minimum height of this mechanical toy, 113.513. So there's an awful lot going on in this part C. Some really cool, I think, graphical things, some cool calculus things. Take the derivative of this function right here with respect to t. That's the fundamental theorem of calculus. Says we have to take v of t and set that equal to 0. Find the places where that occurs. I set up a sign chart. Theoretically, here I evaluate s of t at all of those places, and I could have added in a list and spreadsheet page to do that. The minimum height of this toy occurs at time t equal 3. Tom, very nice problem.
Right.
Okay, I'm going to turn it over to you.
Okay.
Okay. Beautiful.
All right. Well, I will fire up my 84. Hopefully you can see that screen. Okay. Is that coming up, Stephen Curtis?
Yep, that looks good.
Yep, good.
All right, fantastic. Okay. So just want to really kind of mimic what Steve did, but on the 84, and show a few things as we go along the way. I went ahead and entered the function into y1. Save a little bit of time, but that's the same function. But you'll notice that since I'm using the function plotter, my independent variable is x. So x is playing the role of time here. So we've just swapped out this kind of dummy independent variable. So x is time for us. And then y1 is giving us our function for the velocity. And let's just go ahead and do a quick graph. I'll just kind of blindly do my usual default zoom decimal. But let's see. Yeah, actually the Y range is not too bad for capturing what we want, but we really don't have the domain that we want. The domain, we're going to need something that includes the times from 0 to 12. So let me go back to the window and adjust my x min and x max. So I'll give us a little bit of room on the left. I'll put in -1, and then I'll make x max 13. So I've got a little bit of a 1 to the left or to the right of that interval from 0 to 12. And let's graph it again. And now we're seeing a graph that looks very, very much like what Steve had, I think.
So, yeah, pretty cool, Tom.
Great.
Very nice.
Okay. So we've got a couple of integrals that we want to do. Let me actually show, we can do an integral right here on the screen. So let's check that out. So I'm going to go to the Calc menu. So that's the second shift of trace. And we see down there at number 7 is the integral. Let's go down there to number 7. Enter that. And lower limit, I think that first question A was just what's the final position after?
Yes, sir. Yep.
So we want to integrate over that entire interval from 0 to 12. So for the lower limit, let me put in a 0. And the upper limit, let's put in 12. All right.
Hey, how about
so
that?
it not only calculates, it also gives us this visual where it's shaded in that relevant part of the graph. Keeping in mind, so our title today was the Great Accumulator. And so all of the problems today have to do with the accumulation of something. Now this is pretty classic integral application, definite integral application is figuring out change in position from a velocity function. We can think of a velocity function as giving us a rate of change in position over time. And so this integral is getting us the accumulated change in position from 0 to 12. Now, if we were going to do this calculation on the home screen, or that's what I call just the regular calculator screen, but we can do that by using math. Go down to number 9, the integral, Fn int, but it gives us this nice integral template. And let's see, our limits were 0 to 12. And we're integrating, well, we've got that fairly complicated expression for y1, but that's the nice thing about going ahead and storing. Even if you're just doing calculations and not graphing, it's very handy sometimes to store that function in your y1. That way you can just refer to it by that. So I'm going to do alpha F4 to bring up my y variables real quickly. So we'll do y1 of x with respect to x. And there's that value again. Okay.
Tom, one quick question for you.
Sure.
When you did that calculation on the graph screen,
Mm-hmm.
was that definite integral answer stored in the answer key, in the answer box? So that if you had gone back to the home screen, could you say second and answer plus 120?
Let's see. Now, right now, this value would be in
Right,
our
that's in
last
the answer.
answer.
Yeah.
Well, you'd need to redo it on the calculators or on the graph screen, but the answer is yes.
Okay,
Steve.
just curious. Okay.
Yeah. So
that answer, that integral that he did. So if you do that again, second calc.
yeah, let's go ahead and do it
number
again.
7.
Just so we can,
just so you can demonstrate it.
yeah. So we'll do the calc. I'll do that integral again. Number 7, lower limit was 0. And just so that we're not confusing sleight of hand. Let's say we wanted to know, well, how far did it travel between 0 and 3? Okay, let's try that. So I'll do a new one here.
Okay.
So 0 to 3. Okay, there it is.
Mhm.
And actually, that's a relevant number because that's, I think, an answer, or it could contribute to the answer to one of your other questions.
Correct. Correct.
So that's where it's located at time t equal 3. And if I go back to my calculator screen and ask for the last answer, there it is.
That's cool.
Okay. Yeah.
Yeah,
So
that's cool.
That's a nice thing to do, to even if you're doing calculations on the calculator screen, if you're needing to use those numbers in some subsequent calculations, you can get them, retrieve them without having to jot it down and worry about miscopying some of the digits or something.
Yeah, that's neat. I like that. Thanks, Tom. I like that.
Now in part B, we had another accumulation problem, but this one is actually total distance covered. Okay, so we really want to integrate the absolute value of our velocity. So I'm going to save even more time here by just arrowing up to my integral here, hitting enter. That's copied it down there, but what I want to do is replace the integrand by the absolute value of y1. So let me go to that. Oops, let's see. There we are. I'm going to do bring up my math menu, go over to number, and there's absolute value. And oh, there they came up, but it wiped out my y1. I didn't. I should have done the insert key, but no harm done here. Let me just do retrieve y1 again. I'll put of x in there. And then this extra parentheses x out here, let me just delete those. There we go. And there we go. So now I've got the integral from 0 to 12 of the absolute value y1 of x dx. Let's enter this. And there we got the value. So that's the actual total distance covered between those two. All right. So that's just kind of the basics of doing the integral, both on the calculator screen and on the graphics screen. We can get that too. So I think I'll leave it there, turn it back to you, Steve, so we can get to the problem, unless Curtis has spotted any questions that have come up. Or...
I haven't. Nope, none.
Okay, all right. So let me stop the share and turn it back over to you, Steve.
All right, sounds good. Thanks, Tom. Okay, there we go. All right, so this problem number 2 deals with area, volume. And so we have this region R bounded by the x-axis in the graph of y equal to the square root of 1 minus x squared. And you probably noticed that, recognize that function. That's the top half of a circle of radius 1 centered at the origin. And I've got a graph over here on the left-hand side of my screen. And the very first thing is, let's simply use geometry to find the area of that region R. You know, we often have problems like this on the exam where we can use geometry to find the area of certain regions. Often those deal with particle motion too. But we can use geometry here because, let me see if I can scribble this in here, the bottom half of that circle. We know we have a half of this circle. And so the area is 1/2 times pi r squared. The radius is 1. So that's just pi over 2, and I put in a numerical approximation here, and sorry, I went to 4 digits to the right of the decimal. Okay, in part B, now let's get back to some calculus here, and let's use a regular partition with n equal to 10 subintervals of equal length. Let's find a left rectangle sum, a right rectangle sum, a trapezoidal sum to approximate the area of that region R, which is closest to the exact area. Let's find a midpoint rectangle sum. And how does that compare to the exact area? Okay, so here's what I did. There's actually a very nice application, a TNS file for the TI-Nspire on the TI website that's available. I think it's called Riemann sums. And you can actually enter into this application any function you want. You can change the endpoint A and B. You can adjust the bounds, x min, x max, y min, and y max. And then the calculator or the application, excuse me, will automatically find a left, right, midpoint, or trapezoidal sum for n equal to, I think it's 1 up to, oh, I don't remember now, maybe it's around 80 or even 100 rectangles, and it will draw them. It will visualize this for you. Now, of course, as the number of rectangles gets large, the visualization kind of gets filled in there. But this is kind of nice here for 10 rectangles. So look what this did for me on the left-hand side here. You'll notice that there's a slider over here on the right part of this bottom part of the screen. And I can move this slider here to 4 different slots. And I have it set on L for a left-hand Riemann sum. So you can see, excuse me, and on the left-hand side of this, I can drag this slider, and I've set it for n equal to 10 rectangles. So what the application does is it draws in the 10 rectangles. Has it done this correctly? Well, let's see. Over here at -1, A is -1. Let's see, the left-hand endpoint would be right on the axis, so the rectangle is actually right there. That's why you don't see anything. As we go to the next subinterval, the left-hand endpoint, we go up to the curve, and we draw a rectangle with height equal to that value on the curve. There's my next rectangle, and on and on. So this application tells me that the sum of those rectangles, I believe that's a 1.519. It also tells me what the exact, quote unquote, exact area is, why 1.571. It's giving away a little bit here. We know that's the exact area from up above. On the right-hand side of this, of my screen here, I changed the slider to give me a right rectangle sum. N is still 10. And look at this, is very interesting. It tells me the exact same approximation, 1.519. I wonder why that happened. That's a good question for the chat, Curtis. Seems strange that those two approximations would be exactly the same. And then let's see, what else was I asked to do? A trapezoidal sum. So I set my slider to T for trapezoidal, still n equal to 10. And son of a gun, that came back with 1.519 also. That seems really strange and makes me wonder if this application is really working correctly. I wonder if anyone can explain that relationship between the left and the right Riemann sum and the trapezoidal sum. Okay, and one more thing that we were actually asked to do here was to find a midpoint sum based on n equal to 10 rectangles. So again, I've changed the slider over here to M. I've still got a 10, and I apologize, it's a little difficult for me to read on my screen, but I think it's in, is it in orange or yellow? And that came back to be about a 1.586. So of all of these approximations, it certainly seems like the midpoint approximation is the best, is the closest to the exact area. We're lucky in this problem. We happen to know what that exact area is. That's very cool. I would encourage you that if you are using a TI-Nspire to get this application and use this to demonstrate Riemann sums. I think this is very nice, and it's available on the TI website. Very cool. Curtis, one quick question.
That's a cool exercise, Steve. Nobody's commented on the question that you asked, but that's a cool exercise.
It is indeed, isn't it? You can see
to
the
see
rectangles.
that and
Yeah.
think about why you might get similar solutions.
Yeah, why is the left and the
Why
right
are all
Riemann
those
sum the
the same?
same? Why the heck is the midpoint sum, pardon me, the trapezoidal sum is the same? And this
Yeah,
suggests,
yeah,
and I think that Tom has talked about this before, Tom and I have talked about this before, this sort of suggests, did you know, maybe the midpoint sum is a better one to use in many cases. I
yeah.
wonder if that's true. Yeah. This is one of my favorite applications to teach, Curtis, finding the exact area and finding the exact volumes of solids of revolution. I can still remember one of my first presentations about this. If you have absolutely no idea what the answer is in one of these area problems, do you know what you always guess, Curtis? There's a standard answer here. Do you know what you always guess? You always guess 32 divided by 3. And I don't know why that is, but so many of these problems come out that way. And in the solid of revolution problems, if you have no idea what the answer is, you always guess 32 pi over 3. So many of the answers come out that way, and I don't know why that is. All right, let's take a look at another one. Again, one of my favorite applications here. So we're going to take this region R, and we're going to revolve it about the line y equal -1 to create a solid of revolution. We'll call it S. And the region R is also revolved about the line y equal 1 to create a solid, which we'll call C, and we want to know which solid has the greater volume. Well, okay, let's see here. I apologize. I probably should have made this graph on the left-hand side a little bit larger, but I think you can see what's going on. Here's my region R bounded by the graph of y equal f of x, y equal the square root of 1 minus x squared, and the x-axis between -1 and 1. And I want to rotate that region R about the line y equal -1. And well, in my way of doing things, what I do is I draw two radii. I draw a line from the outer curve to the axis of revolution and a line from the inner curve to the axis of revolution. So my outer radius, which I call r sub O, is represented by this line, and my inner radius is represented by this line, which I usually call r sub I, again, for the inner radius. So in order to find the volume of this solid, it's pi times the integral from -1 to 1 of r sub O squared minus r sub I squared. Well, r sub I is easy. It's constant over the entire region. It's just 1. 1 squared is 1. The outer radius is the distance from this curve to this line. It would be at an arbitrary point x. It would be f of x minus a -1. So f of x plus 1. The common error here, make sure you get that squared in the correct place. Off to the right-hand side up here, I have drawn what I think that solid might look like. It's a little difficult to see, but up at the top here is a graph of y equal the square root of 1 minus x squared. I think I've got things labeled correctly along this frame. And I used the TI-Nspire in order to evaluate that integral. Jeepers, I wonder if we could do that analytically. It turns out to be 14.058. How about that? That's very cool. Now we'll hold that aside. That's the volume of my solid. What did we label that, Tom? That was the volume of the solid S.
Yes.
And now we need to find the volume of this solid C. Okay, let's see if I can do that. Now we're going to take that region R and we're going to revolve it about the line y equal y equal 1. So let's see, this solid has a hole in it. So I've got to find the outer radius and the inner radius. I draw my two lines. Here's one of them. Here's another one. It's very small in there. The outer radius this time is constant 1. We square it. That's 1. What's the inner radius? It's the distance between that line y equal 1 and the value of the function at an arbitrary point x. So it's 1 minus f of x quantity squared. I think I've done that correctly. I'm going to plug that into my calculator. I don't have a calculator screen down here, but that turned out to be a 5.681. Perhaps Tom can check me on that with the TI-84. Over here is a reasonable picture of what that solid looks like. I don't want to jump to any conclusions, but of course that solid looks a lot smaller than the one on the previous page, but we have to be careful about scales. But indeed, comparing this value, 5.681, to the one on the previous page, we can see that the solid S has the greater volume. Cool. Curtis, any questions from you about that one? I'm sorry I didn't provide a TI-Nspire calculator page there. Anything at all?
Nope, nothing nothing there.
Okay. Tom, TI-84?
Sure, sounds good, Steve.
Yeah, there you are.
Okay, I think I've got my 84 up there again. Let me just
Yep,
go ahead
looks
and
good,
clear
Tom.
out what we were doing before. And I'm going to go ahead to y equals and just put in that function that we were working with there. I believe it was a very familiar function, that top half of the circle. So square root of 1 minus x squared. Enter that and do just a quick graph here. I'll go ahead and do a zoom decimal window just to get a look. It's kind of small. I think I like a little bit bigger picture of that. So I think I'm going to zoom in. Let's see. If I zoom in right at the origin. Oh, wow, there's good. We got it filled up pretty good. Yeah, very nice. Okay. So there's our function. And I'm going to take a little bit different tack than Steve here. Steve was making use of a program on the, or a TNS document that's available for the TI-Nspire that lets you do this nice visual. Just want to show how you can do without any programs at all. Just construct a Riemann sum and answer these same questions having to do with the right, left, and trapezoidal sum very easily just with the calculator page. So what I'm going to do is go ahead and move to the calculator page and think about, let's see, the Riemann sums we were looking at. I think the interval was from -1 to 1 over that entire stretch that half circle lies over. So I'm going to go ahead and store -1 in A. And I'll store 1 in B. Now I'm going to store 10 in N. That's a number of subintervals that we have. And then I'm going to store one more number. There's one little calculation I want to do, and that is how long is each, or how wide is each of those little subintervals? Okay, so for any integral problem where you have an interval from A to B and some number of equal partitions, that calculation will always be B minus A. So that's the length of our whole interval divided by N. And whatever that calculation is, I'm going to store that in D. And I'm choosing D. That's my delta X, if you will. Okay. There we go. And we can do a reality check. Think about it. Okay, we've got an interval that's 2 from -1 to 1. That's the length of 2 divided by 10. Each subinterval should be 1/5 or 0.2. Well, okay. So now what I'm going to do is just build a Riemann sum. If I go to the math menu and move down past integral, there's a summation. Let's pull that up, see what we get. Oh, how nice. Okay, we actually get a nice looking summation symbol with big capital Greek letter sigma there. Okay, my index, I'm going to choose K, I think. So I'm going to have K run from 1 up to N. So we get all our subintervals. And now let's just think about how we're going to build this Riemann sum. So for each subinterval, I'm going to take a value of my function from a point in that subinterval and then multiply by the width of the subinterval. Okay. So I'm going to put in an expression here, and we'll just kind of think about what it's giving us. Okay, so I'm going to get y1, that's where my function is. I'm going to put in alpha A plus alpha K, that's my index, times D. And then I'm going to multiply. Okay, that's where I'm going to evaluate the function. Then I'm going to multiply that by alpha D. I think I might have, let's see, let's see if I enter this, what happens there.
Nope.
I did something wrong there. So let's go to it, see if we can recover there. Oh, I see. I've got an extra parenthesis that I didn't need there. Okay, let's try. Oh, I see. I have a parenthesis here. I wanted the times D inside of there. Okay. So apologies for.
No, you were all right there, Tom. I don't think.
Oh, I wasn't I? Okay,
Yeah.
let's try.
I think you're okay now. Get rid of that, and I think you're all right now. You want to evaluate that function?
Yeah. Okay, let's try.
I think you're good.
Okay. All right.
There you go.
All right, and that number's looking familiar, but I just want to think about what this is doing. So starting out with k equals 1, notice that the very first thing I'll evaluate is y1 of a plus d. Now, d is just that length of that subinterval. So that's getting me over to the right endpoint of that first interval. And then I'm multiplying by the length of the interval. So I'm getting that rectangle area. And then when k equals 2, I've stepped over to the right endpoint of the second rectangle and evaluated the function there and multiplied by the width again. And then I just do that. So when I get up to n, I'll be all the way over to the right endpoint of the last interval. So that will be actually at b. Okay. So this thing here actually is representing a right endpoint Riemann sum.
Yep.
And with that, I'm going to go ahead and store that answer in alpha r, which is r for right. So right hand. So there we go. Now let's say I wanted to do a left-hand Riemann sum. Well, a way I could do that is just go up here and copy the sum again, and I'm just going to adjust the indices. So instead of starting at k equal 1, I'll start at k equals 0, but I'll just go up to n minus 1. So that's actually the left Riemann sum. Okay. Now, this might not be the best example because of the symmetries involved, and that's what's really happening here. But that's my left Riemann sum. So let me go ahead and store that one in alpha L for left.
Tom, while you're doing that, Curtis, another good question for participants is Tom found the left-hand Riemann sum by adjusting the indices. But I wonder if there's another way to do that simply by keeping the indices the same, but changing what's on the inside of that summation.
Yeah.
Sure.
And then the trapezoidal sum is going to be the average of the left and the right Riemann sum. That's another way to think about computationally what that trapezoid looks like. And we're here because these are the same, we shouldn't be too surprised that if we did add these together, alpha L plus alpha R, those were my left and right Riemann sums. and divide by 2. Well, since they're the same, we're getting that same number 3 different times. Okay. Now, this actually relates to your question, Steve, for the audience, is let's say I wanted to get a midpoint sum.
Yeah, what do you do now?
All right, well, I'm going to go ahead and get this left Riemann sum, copy it down, and I'm going to edit it a little bit. Okay, this is, instead of starting at the left endpoint of the first interval, that's what's going to happen with when k is 0, I'm going to go halfway through that interval. So I'm going to make this a k plus 1/2. Now what that'll do is when k is 0, I'll get a plus 1/2 times d. That'll be halfway through that first interval. When k is equal to 1, it'll be a plus 1.5 times d. That'll land me into the halfway point of the second interval, the midpoint. And so each time k goes up, I'm just moving over to each midpoint. So this should give me that midpoint sum. Let's give it a shot, see what happens. I think that's looking good. That's very close to what you had.
So be careful too, Curtis, if you were going to generalize this, what would that 1/2 be? I mean, it just happens to be, is it all, well, let me rephrase the question. Is it always k plus 1/2? No matter how many intervals we have, no matter what the value of d is? Is that true? Just something to think about.
Yeah, I like it.
So I think what I love that program or document that Steve showed, and there are some Riemann sum programs for the 84. But this is just, I would encourage teachers. This is basically kind of taken. Sometimes programs can be almost too quick to give us the answers, and this just want to pull back the cover on the black box. This is exactly what a Riemann sum is. We're just calculating it from scratch and seeing what those values are. So, okay, all right, and of course, with the integral available, we can do some of these other integrals. Like I'll just do one of the volumes of revolution that Steve looked at. So let's go ahead and pull up the integral. Let's see, we had from -1 to 1. And actually, let me back up and put on the outside of that integral. We want to multiply by pi. So let me go ahead and hit the pi times the integral there. Very good. And then I think that integrand expression we had was, remember, we have it in y1. So we'll do a y1. Of x plus 1. This is the one where we're rotating around the line y equals -1. So
good.
Our function graph is an extra 1 away from that axis of revolution. Okay, and then once we evaluate that, we'll square that. And then we'll subtract 1 squared. Could just put in 1, but just to emphasize that that's that inner radius squared.
Yep, good.
Great with respect to x. And if I haven't made some error in typing in things, I think that's what we got. And it should come out to be 14 something, I think is what Steve got. It's working away.
Hey, how about that?
I think that looks really good. All right.
Yep, sure does.
So, and again, this function wasn't too complicated, but if you had a complicated expression for function and for your function, and you're doing several kinds of integrals with it, it's really handy to have it stored there in y1, where you can just refer to it and see those things at play. Okay.
Yeah, we haven't talked about this, Tom, but one of the AP exam tips is on the calculator active portion of the free response. If you're given a function, a named function f and g or f, g, h, whatever, one of the first things you should do is type it carefully into your calculator in y1, y2, right?
Absolutely.
So
Yeah.
you don't have to keep typing it over and over again, and you can use the symbol y1 or y2 in any other calculations. Yeah, I agree.
Right.
Yep.
Yeah. It's also perfectly okay to you come up with an expression that you want to refer to later is to come up with your own name for it. If you declare it right there on the exam, say, hey, I'm going to call g of x equal to this.
Yes.
You can refer to g of x, and the readers of the exams they'll take you at your word.
Yep.
Whatever you declare g of x to be, that's the way they'll read it. So
Right.
Yeah, very good.
Now,
Yeah.
I like the fact that by doing this on the 84 the way you did, Tom, the students are really demonstrating sort of that understanding of the structure and the setup and the
and
I
fluency
think
of
that's
notation is another thing, I think.
yeah, I
Yeah.
think that's really nice.
Yep.
Okay. Well, I'll stop the share and turn it back over to you, Steve.
All right. Here we go. There it is. Okay, we're back to number 3. I like this one, Tom. We haven't done one like this in a while, I think, that has to do with accumulating the total mass of an object, or often they talk about a solid metal rod here in typical examples. Here we have a cable that has length 12 meters, and it's laid out in a straight line along a metric tape measure. How do you like that? One end is at the 4-meter mark, and the other is at the 16-meter mark. And the density of the cable between 4 and 16 is given by this symbolic expression. There it is. And D is measured in, I think it's kilograms per meter. What's the total mass of the cable? Well, to repeat something that Tom said a moment ago, we're talking about the integral as an accumulation function. And what we're really doing here is we are accumulating the density of this cable from 4 to 16. And we do that with a definite integral. So I wrote this function d a little bit differently in here because it seemed to me that I could solve this problem analytically. So it's an integral from 4 to 16 of 1/8 x to the 1/2. Again, I am accumulating the density of this cable from x equals 4 to x equals 16. Well, let's see, the way that I did this, I think, was I brought the 1/8 out in front. Constants pass freely through integral symbols. And integrating that expression is simply, I think, the power rule, backwards power rule. We often think of it that way, 2/3 x to the 3/2. Plugging in these upper bound, this upper bound and the lower bound, and a little bit of simplification. And when I'm all done, I think I got a 14 divided by 3. How about that? And just to show you how the TI-Nspire does this, I'm still amazed by this, still love this. I define this function d, there it is, 1/8 square root of x. When I integrate from 4 to 16 of d of x, I get the exact symbolic answer, which is still really cool to me, that the calculator does that and gives you the exact value wherever possible. It does all the integration in the background, all the substitution in the background, and tells me the final answer is 14 divided by 3. That's very cool. What's the average density of the cable? Well, again, another application of the definite integral. This is an application of the average value, and so what we would do is find the integral from 4 to 16 of the density and divide by 1 over upper bound minus lower bound, 1 divided by 16 minus 4. So this one isn't so bad in light of what we just did a moment ago. There's the 1/12 from the 1 divided by 16 over 4. And this is very similar to the integral, the definite integral that we just did a moment ago. I looked back and saw the answer was 56. I did a little bit of simplification, and I think I got a 7 divided by 18. And just to double check this, on the TI-Nspire, there's my 7 divided by 18. There's my setup for the average value of that function. cool. I think there's one more here, part C.
So Steve, is that just 1/12 of the total mass of the cable?
It is indeed.
Ah, okay. Oh, that makes sense. So this if you had a uniform cable with constant density, this would be
Yeah.
what density you would need if it would have the same total mass. Okay.
How about that?
Yeah, cool.
Yeah.
I like that.
I really like this part C. This is often one of those questions on the exam where they might say set up but do not evaluate. But you know what, son of a gun, we can evaluate it because this one isn't too bad analytically, and we can even do this with technology. It says at what point x equal k would the cable be cut into two pieces to have exactly the same mass? So I'm going to draw a little picture over here. Here's my cable from 4 to 16. And we want to find this place somewhere around here. I don't know where it is, this point K, where the mass of the cable is exactly the same from 4 to K as it is from K to 16. So here's a way to attack this. I know that the total mass of the cable is 14 divided by 3. I think that comes from part A of this problem. So I have to find this value K so that the integral from 4 to K of d of x dx, or remember, we're finding the accumulating the density of that cable from 4 to k, and I want it to be half of 14 divided by 3, which I think turns out to be 7 divided by 3. Cool. So let's see here. I'm going to find the antiderivative of x to the 2/3, of x to the 1/2. There we go. There's the 2/3 x to the 3/2. I'm going to evaluate this at an upper bound of k and a lower bound of 4. And I did a little bit of simplification here. Here is an expression, or pardon me, an equation in k, one equation and one unknown. It seems like we ought to be able to solve this. So I multiplied both sides by 12 here. I got a 28 on the right-hand side. I added 8 to both sides. And then I raised both sides to the 2/3 power to isolate k. I got a 6 times the cube root of 6. How about that? And this is really cool on the TI-Nspire. Look at this. There's a built-in solve command on the Nspire, and it will actually work with an integral expression. I typed in the integral from 4 to k of d of x dx. Remember that my d was already defined. Set that equal to 7/3. Kind of hard to see, but there's a comma in there. And I'm telling the calculator to solve that expression for k. And son of a gun, it came back with the exact same value, 6 times the cube root of 6. That's unbelievable that works.
That's a really nice
That is very
feature
cool.
of the CAS.
It is, Curtis. Very nice feature of the CAS. Yeah. Yeah.
Of the Nspire.
Tom, should I just end by talking a little bit about number 4?
Yeah, I think we're about out of time, Steve.
Okay.
Sure,
So we'll just set up number 4 here. This is a nice applied problem, which involves a Riemann sum. So we have a contaminant spilling into a holding pool, and we know the rate at which it is spilling. We've got the rate at selected values of time t. We want to use a left rectangle sum determined by this table to approximate the total amount of contaminant spilled. And again, we will post these solutions, if not tomorrow, then the next day. There's my left Riemann sum based on this table. This left Riemann sum is actually an overestimate of the amount of contaminant filled. It's an overestimate because we know that the rate is a decreasing function, very often a question on the exam. So we know that this 4720 is an overestimate. And then in part C, we actually have this team of workers that comes in and they start cleaning it up at time t equal 12 hours. And we know the rate at which they are cleaning this up is given by this function. And so how much would they clean up? from t equal 12 to t equal 30. They could run this from t equal 12 to t equal 30, and they would have cleaned up this amount of the contaminant. And so the final question is a very good question in context. Do we know whether or not they would have cleaned up all of the contaminant? And the answer is yes, they would have, because this is greater than or equal to this 4720 found in Part A, which we know is an overestimate of the total amount of contaminant spilled. And so these workers who came in here cleaned everything up. Very cool, Curtis, a lot of fun. I think you're on mute, Curtis.
You're correct. I am on mute. I was just testing to see if you guys were paying attention.
Good.
No,
Yep,
it's
good.
great content today. Both of you guys, I appreciate that. And I'll just drop my email in the chat box here. If anybody is out there looking for the professional development certificates, I will send you a link to generate that. So please, make sure you're looking for that. Yeah, we are really excited to be doing these sessions a little earlier in the afternoon. Give you guys time to go and watch the sporting events. I won't say football because I think we've passed football season, although there's a relatively large game maybe happening here
Yes.
coming up this coming weekend. Something's going to happen. Anyway, want to make sure that you guys have a chance to download the teacher document. I'll have that loaded tomorrow. And then, yeah, we'll be back here exactly 1 month from today, 4 weeks, on March 2nd. So be looking for that. Steve will make a post out there in the Facebook page.
Absolutely.
Yeah, really excited. Anyway, I hope you guys have a great week, and we will talk soon. All right, guys.
Curtis, thank you so
Wayne.
much. You guys are so good to work with.